Hello everyone. Today we start a new chapter in this course on enablers of cloud computing. In this chapter, we are going to discuss what technologies enable today's cloud computing technology. Specifically, we are going to talk about virtualization, and virtualization techniques that together uh, is an important part of what is nowadays called cloud computing. So this part will take almost half of this chapter, and then the rest of the technologies will take less time in this course. We will talk about service-oriented architecture and the market and commercial aspects of cloud computing. These are all the differences that were made in cloud computing with respect to earlier versions of distributed systems such as clusters and grids. Okay, so let's start with virtualization. Before virtualization or without virtualization, what we have is a hardware system uh, and an operating system. So all of you are familiar with this kind of architecture, and all of our computers work in this manner. Then the application is on top of the operating system. Application talks to the operating system, and operating system translates those commands of the application to the hardware based on the machine language, based on the instruction set of that machine. So this is the conventional way of operation in a given computing system. So the problem is that the applications are operating system dependent, and operating systems only can work with a certain hardware. So this coupling of the application and operating system and hardware makes it very inflexible and makes it difficult to utilize computers for different types of users, because different users, specifically in the context of cloud, would like to use different platforms. When we say platforms, means for the most part the operating system. All right. Therefore, one of the changes that happened in cloud computing was the use of virtual machines. I'm saying use, not the emergence, because virtual machines were there already in the computing industry for many years, even before cloud or grid. It dates back to 1970s and around that time. However, the use of it in distributed systems began in early 2000 in grid systems and later transitioned to cloud systems. Using virtualization platform or a virtualized platform, we have to use a software layer called the VMM, Virtual Machine Manager, or what is also known as hypervisor. You may hear also the word virtualizing software. It's a software layer on top of the hardware machine. What it does is basically decoupling the operating system from the hardware, from the underlying hardware. In other words, this virtualizing software or VMM can understand different instructions that are given by different operating systems, and then it has the ability to translate them to the underlying hardware, to the instructions of the underlying hardware. The advantage of this method of operation is that we can have multiple operating systems on the same machine, because those different operating systems, in whatever way they are designed, as long as they are compatible with the virtualized software, with what is so-called hypervisor, they can talk to the hypervisor, they can send their commands, and those commands can be translated based on the underlying hardware by the virtualized platform. The advantage of of the virtualized platforms and virtual machines means basically an operating system that operates in a virtual on a virtual machine, not on a real machine, which basically means the machine that is offered to it by the virtualized software, by the VMM or hypervisor. The advantage is that we can have multiple operating systems on the same hardware. The other advantage is that the uh, virtual machine is decoupled from the hardware, from the underlying hardware. Like that, if we uh, like that, we can detach the operating system from the underlying hardware. And if we have other options, we can transfer this virtual machine, this operating system, to another machine. What is so-called migration? So another good thing about virtual machines and virtualized environments is that users do not have to make any change in their application. In other words, if you develop a program for a normal operating system, let's say for Windows, to be run on a normal host machine, I mean on a physical host machine, on a normal machine, the same code can be executed on a virtual machine, on a Windows machine that is running on a virtual machine. So that's the advantage. You do not need to make any change in your code base because of the underlying virtualized platform. So I guess I explained these points in the slides. Uh, so basically, this point is important. Mapping of virtual resources to real hardware resources is done by the virtualized platform, by that hypervisor. So what happens is that your operating system and similarly your application does not know about the underlying virtualized platform. They think that they operate on a full machine, on a real machine. They don't know that there is another layer under them that virtualizes or abstracts everything. For example, you may have a machine with 4 cores, and then you can create a virtual machine that uses 2 cores, and let's say half of the main memory. So this would be your virtual machine 1. Your virtual machine 1, let's say it's a Windows operating system, does not know that in fact there is a machine with 4 cores and let's say with a huge memory. It thinks that there is just a machine with 2 cores and half of the memory that is allocated to this uh, virtual machine or to this operating system. So this abstraction, this illusion is provided by the virtualization software, or what is so-called the hypervisor. All right. So this is what I was talking about. So now we have the application. Sorry, in the traditional model, we had application, we had the host operating system, and we had hardware. Now what is happening is that we still have the hardware, the real hardware. We have the VMM, the hypervisor or VMM, and then they create some abstraction view of those resources that the guest OS means the virtualized operating system or the operating system running on the virtual machine does not know about the real software, the real hardware. They just see this hardware, and then application accordingly plays with this one. This high-level abstraction is provided by the virtualization software. All right. The next question is that how to do virtualization. There are different ways, different technologies, and different tools for doing virtualizations. Or in more simply speaking, there are different hypervisors. Some of the important ones, well-known ones, are VMware, uh, KVM. You may have heard of Zen and things like VirtualBox that are more well-known in the user's side, on the end user side. All right. We can categorize the architectures, the way the hypervisors operate in 3 ways. Let's assume this is the conventional form of operation uh, for the systems that we have hardware, operating system, and applications. Then one way to do virtualization is known as native VM. In this form of virtualization, we have the hardware and the hypervisor comes exactly on top of the hypervisors. In other words, sorry, on top of the hardware. In other words, in this system, we do not have host operating system. right? So there's no operating system for the physical host. There's just a VMM on top of hardware, and then that can support different operating systems, guest operating systems, and then we can have our applications. Some versions of VMware, known as VMware ESX, works or ESX server works in this fashion. This fashion is also known as full virtualization. Another way of operation is entirely opposite. So it has hardware again, it has the host OS, and then on top of the host OS, we have the virtualized software hypervisor. And then on top of that, we have the operating system. I should draw something here. Operating system, guest operating system. And then on top of that, there is the guest application. All right. This is the known as hosted VM. And this is the one that many of you are familiar with. Things like VirtualBox work in this manner. And I know many of you install VirtualBox on your machines. You have your host operating system. Let's say you have a Windows machine, and then you install, let's say, VirtualBox on top of it. And then you can install, let's say, Linux on top of that virtual machines provided by the VirtualBox. And then within that, you can do whatever Linux application you like. All right. Although this is very popular in the user's domain, on the cloud side, there is another way of operation that is kind of the hybrid between hosted VM and native VM. That is called dual mode, or even more popularly known as paravirtualization. So paravirtualization is the case where, again, we have hardware and we have host OS, but VMM is quite a bulky thing that becomes part of the host operating system. In fact, it becomes part of the kernel. So it is in the system mode. It's not in the user mode. And part of it is in the system user mode, part of it is in the system mode, and becomes part of the kernel. And then on top of that, we can have our guest OS, and on top of that, we can have guest applications. So this fashion of operations, known as paravirtualization, is the most well-known nowadays, the mostly used in cloud data centers. Specifically, there is a hypervisor known as KVM that nowadays is very popular and is used by many cloud providers, including Amazon Cloud. There are other versions, other hypervisors such as VMware Server and Zen that also operate in this paravirtualized manner. All right, let's assume that the virtualized platform has provided us with the concept of VMs. VMs means virtual machine, means like the operating system that you use in a virtual manner. So what abilities this virtualized environment give us? So one ability, we call it VM primitives, the basic abilities. One ability that it gives us is the ability to multiplexing. So by that, we mean that the same hardware system can be used by different operating systems. So look at this case. For example, we have hardware 1. On top of that, we have our hypervisor. And on top of that, we can have multiple operating systems. So it seems that this hardware is multiplexed between these different operating systems. So this is one advantage that we kind of implicitly talked about in the previous slides. Another operation that is enabled by virtualized platforms is known as suspension. So you may have heard of hibernate. So suspension and hibernate are the same thing. So using VMs, you can, or virtualization, I just informally call it VMs. Using VMs, we can suspend the operating systems or the virtual machines, which means that we preempt all the resources allocated to them and free the space for other systems, or for whatever reason we may like to suspend slash hibernate some of the operating systems. All right. And then keep an image of it on the storage, and at a later time, we resume its operation. All right. So, and then the resumption of the uh, operating system of the virtual machine can happen either on the same machine, or it can be done on another machine, as we could see in this last figure. So in this case, what happens is called the migration. So basically, the operating system migrated from the source place to a destination place. For that purpose, it first got uh, uh, suspended. An image of it was created and on the storage, and then it is resumed on another machine, which is basically the migration operation. So I talked about migration before. This has been one of the most difficult problems that uh, people in distributed system have been dealing with, but thanks to virtualization platforms, this is doable now. All right, I want to mention one more point. If you are going to do the migration, and if you are going to use this virtualized platform for your cluster or your cloud, you should make sure that there is a shared storage in place, right? So we should have a shared storage across our hardware machines, across our machines, right? Like that, you can make a snapshot, basically make an image of what is going on in memory, known as virtual machine, basically virtual machine, the state of it, and then persist it on the storage, and then resume it on another machine which has access to the same storage. All right. Another kind of magical operation that was very novel for virtual machines is known as live migration. So we can imagine what I explained earlier as a cold migration, where you suspend a VM and then resume it somewhere else. Alternatively, you can do a live migration in which the VM is copied, is moved to another machine seamlessly. So the users of that VM do not even realize that the transition is being happening. So this is extremely useful in many use cases. For example, assume that you have an online business or an e-commerce website, and then your clients are keep purchasing items from your website. Of course, in this case, you don't like to see any downtime because of migration in your servers, and of course in your e-commerce application. Uh, in this situation, live migration is extremely useful because your service, your e-commerce application can move to another machine for whatever reason. For example, you want to do some maintenance on the original machine seamlessly without knowing that the transition is happening. All right. I again note that all of these primitives require the shared storage. Without shared storage, none of these operations are possible except multiplexing. There is one other operation called snapshots. Well, snapshots is very similar to suspension, and in fact, this is the same thing. But I would say snapshots on VMs are very much like save as operation on file system. And the advantage of it is when you want to do changes that you are not sure if you want to lose the earlier version or not. So basically, if you have a working virtual machine, you can and you are going to, let's say, install some packages or make some changes, and you are not sure if your application, sorry, your operating system will remain in a working state or not as a result of those changes. So you don't want to lose whatever you have done so far. So you can make a snapshot of whatever you have done, and then you keep changing on the existing version of your operating system of your virtual machine. And then later, if you mess up with something, you can basically trace back to an older version and basically keep working on the older operating system. All right. Those of you who have had operating system course are familiar with the states of a process in an operating system. Similarly, we have a cycle, a life cycle for a VM that is created in one machine. I would like to note that VMs from the host OS perspective. When I say host OS, means the machine that is the physical machine and the OS of it. From the host OS perspective, VMs are nothing but just processes. However, if we go deeper, we can consider the following life cycle for VMs. First, your VM requests are queued. This time is generally negligible in small systems. Then your VM enters the running state. That is when your VM is booting up and you can use the operating system of it. Well, you can use it for whatever amount of time you want, and then you may decide to suspend that. So it enters the suspended state. And then you can resume it on the same machine or on another machine. You can, in the case that you want to run it on another machine, it goes to the migrating state, and again it goes to the running state. Another way we can do migration, as I mentioned earlier, is the live migration. Note that in this case, we have a transition from the running state to the running state. And you can do this until you decide to terminate your virtual machine. All right. Another operation that we do on that we can do on a running virtual machine is called pausing it. Pausing is very similar to suspension. However, it's a lighter version of that. In pausing a virtual machine, we just preempt the CPU allocated to that VM temporarily. So the VM preserves all other resources except the CPU, which is the main resource, probably for a short time for some important task, and then later we can resume to the running state very quickly, and the VM can continue as a normal platform. All right. So once you create a virtual machine, let's see what happens on the disk. In other words, what files are created as a result of running a virtual machine. So one of the things that are created is called the configuration file, or more commonly known as VM template. A VM template is a file includes some metadata about your virtual machine. Like, for example, the number of cores it has and the amount of RAM it has, and this type of metadata about your VM. So you also have another large file which is called VMOS disk. So this is the largest file that you deal with when you work in a virtualized platform. So basically for each virtual machine that you have an OS disk, which is a very bulky file because it includes the storage that you allocate to that VM uh, and the packages you installed in it. So it's a bulky one. So another thing that you generally see is the log file, where the messages resulted are stored in it, and that's good for error catching and debugging the system. So snapshot disks, in case you want to do snapshots that I talked about, and NVRAM disk, which is basically NVRAM means non-volatile RAM or non-volatile memory, which basically is the image of your virtual machine in case you do suspension, as we talked about earlier. All right. I want to talk a little bit about live migration because you may ask yourself how this magic of live migration be possible. So here I'm going to explain the steps in doing a live migration. Let's assume that we have a virtual machine running on host A, and our goal is to moving that to host B, but we don't want any downtime, and we want our services being offered using that virtual machine keep running. So here is the algorithm to do so. In the first step, we create and initialize the space on the target machine. Let's say in this case on host B, we reserve all the memory required for copying and all these things. So in the next step, the copy operation starts. Please note that we are transferring the virtual machine. We are not transferring the disk image. The disk image is generally multiple gigabytes, and it is very time consuming to transfer that. So it is not possible, at least at the current time, to move the VM image. What we are talking about is moving the state, the running virtual machine, to another node in your cluster. All right, so we are talking about the memory. When I say memory, means the RAM content of your virtual machine, or the RAM footprint, or the footprint of your VM on the RAM. So you know that the data in memory are kept in pages, which means basically partitions, small partitions of memory. So what happens in stage 2 is that the memory contents, the memory pages of the VM in host A are copied to the destination host B. Well, while this operation is done and copying all the pages of the VM to the destination machine, it is possible that some of the pages of the in this interval of copying, it is possible that some pages get dirty, means they get written on. So we have to update those pages that have got dirty, which means they have got changed. So in the next round, we just copy the pages that have got changed since last time. And then this time is definitely much shorter than the previous time. But again, although it is short, it is possible that some pages have got changed. So again, in the next round, we copy those have got changed. And we iteratively perform the copy operation until there is no dirty page. In that stage, which is stage 3, we do the stop operation and basically uh, do some further works, including the network redirection. Let's say the request coming to the old host now have to be redirected to the new host from the network perspective. So those type of affairs are done in stage 3, and then the change is committed, which means that we are transitioning to the new state. And in stage 5, it is activated, the destination machine is activated, and we can run on the destination machine. So please note that before the commitment state is done, all the operations are still done. Before the stop, before stage 3 and stage 4, all the operations are still done on machine A, on host A. So the only downtime that the user observes is for stage 3 and stage 4, which are minimal. So this figure shows the slowdown resulted from a live migration in a, in a more accurate way. We can see that uh, the, at this stage, the VM is operating as a normal machine without any change in it. So at this point, the migration started, and there is a slowdown in the throughput, in the number of requests that the machine can handle. And then this is the part that the iterative copy is being done until the very last step, which is the minimal downtime, and this is when we go back to the host B and basically start from the destination machine. So we can see that the downtime is almost negligible, 165 milliseconds in this case. All right, now we are convinced that virtualized technology is great. It gives us a lot of flexibility. And now we are going to talk about how these can be helpful in the context of cloud. Specifically, how can we build virtual clusters as opposed to physical clusters using virtual machines? So a physical cluster is what you build, it is what you can build, let's say, using your Raspberry Pis or several machines that you have. But a virtual cluster is a set of virtual machines that you created, and you connect them together and build a virtual machine and build a virtual cluster. So these virtual machines can potentially come from different physical clusters. So you potentially may have different clusters. Let's say in a case of a cloud, which is a huge data center, you may have several clusters, and you can create a virtual cluster where each virtual machine is coming from one physical cluster. So this is an advantage provided by the uh, uh, virtual machines. Another advantage is that the configuration of your cluster is very dynamic. In other words, for example, in virtual cluster 1, you start off with 12 virtual machines. And in between, because there is less load in the input, so you can probably shrink it down to 4. And then at a later time, when you have a peak demand, you can again stretch to 12 or even more number of VMs. So uh, this is called elasticity that is provided by the virtual machines as the underlying platform. We cannot have elasticity in physical clusters. All right. So I guess I talked about these points. VMs can be replicated on multiple servers for the purpose of distributed parallelism and fault tolerance. The size of virtual cluster can grow and shrink. This is called elasticity. The boundary and size of virtual cluster may change over time. New VMs can be created. The fault tolerance can be achieved because if some VMs cannot perform well, you can just terminate them and replace them with something with a better performance. And several other advantages resulted from virtual clusters. One of the very important advantages is called consolidation, server consolidation. So the thing is that when we work with virtual machines in clouds, we generally over provision them. In other words, if, for example, we have two requests that can be hosted on one machine, we probably prefer to provision them on two different machines. Although we have enough resources to hosting them on one machine, we may prefer to host them on two different machines because we do not know how much load they are going to accept, and then we don't want them to suffer from sharing the same platform. So we may kind of do a wasteful allocation and allocate them on different machines. However, the side effect is uh, energy consumption. So we know that one of the main problems in cloud systems, in cloud data centers, is their energy consumption. So this wasteful or over provisioning of VMs can result in high electricity costs. Specifically, consider the situation that the VM is created but is not being used or it's very lightly used. So in that case, we can take an opposite approach and consolidate VMs on one or few servers and turn the other servers down, other physical machines down to save energy. So VM consolidation, this is basically done via VM migration from the technical point of view, and it is just doable because of virtual machines. And that is one of the reasons that clouds use virtual machines, because it helps the cloud providers to save a lot of costs because of their flexibility in migration. All right, so using all these advantages of VMs comes with a cost. In fact, what I mean is that if you want to do consolidation or migration or suspension, all of these operations, although they're available, but you cannot do them manually in a large scale, let's say in a scale of a cloud. So you need a platform to help you. Those platform is, in addition to hypervisor is just required for one machine to create to give it the ability to create VMs. So we need something beyond that in a cluster scale, in a data center scale, that manages all these hypervisors and with VMs within them across a data center. We require something for VM scheduling. So for a given VM request, where to allocate it. We require policies and a platform to apply those policies for VM consolidation. We require policies for fault tolerance if a VM is not performing well, terminating it and replacing it with something better. Load balancing and image management. So that last point is interesting because just be careful that a cloud provider supports numerous users. Each user has one or even more images, VM images, the bulky part, the disk image, and managing all of them is a nightmare if you want to do them manually. So the platform that we use also can take care of the VM image management and replication of them and all the implications of having so many VM image. All right. So specifically with respect to VM images, we have the VM image itself that I talked about. That is the bulky part that includes the disk and all the packages you installed on your VM. And we have another thing is called VM template that I talked about. That is some metadata about your VM. Okay. For example, a VM image can be a Linux operating system and having Apache and MySQL and PHP on top of that, plus some, let's say, 10 gigabytes of disk and stuff. So this is the image itself. However, we have a VM template that tells the hypervisor what type of VM, what type of resources to be requested for this VM that is going to be created. So, for example, we may require for one gigabyte of memory, 2 cores of CPU, and 1 gigabit per second of network. Next time, I may create a VM template with 4 gigabyte of memory and 4 cores, and let's say 10 gigabit per second network. So that is the template. That's the VM template that basically tells the hypervisor what type of VM to be created out of that image. So once you have the image, you can create different VMs with different resources. This is an example of a configuration file, a template that tells it what is the name of the VM, how much memory it is assigned, how many cores it is assigned, what is the virtual disk address, and things like that. All right, so the creation of VMs on from the VM images, from the base image, the creation of images is called instantiation, VM instantiation. So basically, from one VM image, you can create numerous images, theoretically unlimited number of images, sorry, not unlimited number of instances can be created from one image. So the instance is in memory, it has a state, it is in the memory and you work with it, you install something in it, you can work with it. But VM image itself is a passive concept, it's stored on the disk. So what happens is that on each machine in your cluster, you can create several VMs. So although it is very good, although it gives us a lot of flexibility, although it gives us a high utilization for our resources, but it's not all good. There are some disadvantages. Specifically, there is an issue called multi-tenancy. So multi-tenancy is when you have multiple when you have multiple tenants on one hardware, multiple virtual machines on one hardware. The disadvantage is that although these VMs are isolated from each other in the software level, however, in the hardware level, or for resources, for the underlying hardware resources, they compete with each other. Let's assume that you live in an apartment as opposed to living in your own house. And because of the apartment is like kind of a multi-tenancy, right? So you can imagine in apartments you face more difficulties or sometimes more slowdown. For example, you can imagine a situation that you want to use the elevator, but the elevator is being used by another neighbor. So that slows you down. So similar things may happen in the case of a cloud system. So maybe you are allocated, your VM is allocated next to a VM that is very I/O intensive and extensively utilizes I/O channels. So if you want to do some I/O operations, you need to wait for a long time to be able to catch the I/O channels. So this is different with the circumstance that your VM is allocated on another machine who doesn't have any neighbor, or the neighbors are not very active in I/O. So multi-tenancy injects a lot of uncertainty to your VM. So it is expected that in a real cloud platform, the performance of the VM that you create fluctuates a lot over time. So speaking of scheduling in virtual machines, there is a lot to talk about, which is of course beyond the scope of our class. I just want to mention that cloud VMs use space sharing for scheduling VMs. In other words, if, for example, your machine has 4 cores and you want to create a VM with 2 cores, so or let's say 2 VMs, each one with 2 cores. So this, in fact, you are space sharing your resources. So you allocate 2 cores to one machine, to one virtual machine, and 2 cores to another virtual machine. So this is called space sharing. Or it might be better understandable on the memory, where part of the memory is yours and part of the memory is for the other virtual machine. Please note that space sharing doesn't necessarily mean that you are always getting the same resources, but it means that you have a fair share, the requested amount of resources on that hardware. However, it is possible that in the first, let's say, time slot of the scheduling of your virtual machine, because I said that virtual machine is nothing but a process from the host OS perspective. So it is possible that the host OS allocates this process, this virtual machine, on core number 1 and core number 2, but in the next scheduling cycle, it is allocated on core number 6 and core number 7. So it is possible, and it is possible to make it fix on a certain cores. This is called pinning, CPU pinning. CPU pinning is the operation, is the system admin operation basically, that you say to the operating system of the host machine that, hey, this VM has to be allocated on just core number 1 and core number 2. Please do not touch it. So the good thing is that in this case, there is less scheduling overhead, and the performance would be increased a little bit. All right. I talked about server consolidation, so I skipped this slide. All right. So far we are convinced that there are a lot of things to do to manage virtual machines and hypervisors if we want to configure our cluster / cloud with a virtualized platform. We need a platform to take care of scheduling, load balancing, consolidation, VM image management, and many other things. So many platforms so far have been created for these purposes. We can call these platforms as cloud middleware. So if you want to build a cloud, you need these middlewares. Of course, you need to make your machines first virtualized. Each machine first needs to be virtualized using hypervisors and VMs. Then you use a cloud middleware across the whole cluster that manages those hypervisors. Let's say in the case of Slurm, you had the Slurm that was managing the whole cluster. In this case, the cloud middleware does that. So if you want to build a cloud, basically you need to install this cloud middleware in addition to installing hypervisors on each of the machines. So several platforms have emerged, have been created so far, but some of them are more popular than others. Nimbus was one of the pioneers in the open source domain. And then Eucalyptus, these are more academic ones. The industrial ones are mostly not open source, so that's why we do not discuss them extensively here. So Eucalyptus was an interesting platform that was active at some point. I guess it is still active, but at that point it was more active. And the goal of it was to creating compatibility with Amazon cloud services. So whatever service they were providing, they were offering a similar one. Like that, the advantage is that you can create a cloud, a private cloud, your organizational cloud system, and you just use the same system model, the same application, the same system admin policies that you use on the cloud. So that is the advantage of Eucalyptus. There were other technologies like OpenNebula, that was a hypervisor, cloud middleware, or virtual infrastructure manager is also called, uh, and vSphere 4. But after all of these, another platform came to play called OpenStack. I guess it was around 2011, 2012 that OpenStack came to the picture, and ever since it has been the most popular open source platform for cloud providers. So even many industrial clouds nowadays use OpenStack. It's a very active and very popular platform for clouds. Okay, let's look at Eucalyptus a little bit. So basically, it enables us to create virtual clusters. It mimics AWS. AWS means Amazon Web Services, Amazon Cloud. And it enables us to create a hybrid cloud, which means the combination of local organizational cloud and a public cloud, like those offered by Amazon. All right, in a schematic view, we can imagine Eucalyptus as something like this, that let's say we have two clusters, cluster A and cluster B, and then we have multiple nodes, multiple machines on each cluster. So each cluster has an instance manager. Basically, it has its own hypervisor and virtual machines. It is called instance manager in the context of Eucalyptus. Each cluster has a group manager, which is in charge of managing those hypervisors and VMs within that cluster, knowing which machines have available slots, and doing monitoring and things like that. All right. And then the cluster manager is the one that deals with the users. So the users basically send their request to this central cluster manager or cloud manager, and the cloud manager orders, or based on the information that it receives from the group manager, decides where to allocate that request. And then once the request is handed over to the group manager, it will allocate it on a certain machine. All right, this is the OpenStack architecture. This is for free study material, so it's up to you if you want to have a look on the structure of OpenStack. But I want to mention that it follows the same structure. we have the infrastructure services, we have the orchestrator that coordinates this infrastructure, and we have the cloud manager that basically interfaces with the user. All right, some more information about OpenStack. And then by knowing these things, now you can have a good picture of a cloud platform. So basically, uh, what is the stack of tools that are used to create a cloud system? This you can consider as the cloud architecture. Therefore, this is an important slide because it shows you the how to build a class. Sorry, how to build a cloud. So in the very bottom, on each machine, we have the hypervisor, generally KVM or VMware. These are the more popular technologies. This is on each machine. You have to have your hypervisor, and then you can have your VMs. All right. And generally, within one cluster, within one cloud, we use one type of VM manager. For example, Amazon may say that, hey, I'm just using KVM for all my machines. So it's not like using multiple of them. It's rare. So the next layer, which we can call it some group manager level, is the VI manager, or things like OpenNebula, or even more popularly, OpenStack. And then we can have the higher level tools like Cloud Manager, like Eucalyptus, or even Amazon, that basically work with these guys, or sometimes they do directly work with the underlying layer. But I would say that these OpenStack and OpenNebula are more tuned to work at the cluster level, and these Eucalyptus and Amazon, the interface, the high level, is good to deal with the users. Now, this the cloud management basically interfaces with the users. The users can be individual users, the users can be other clouds when we want to have a federation of clouds, or the user can be a platform as a service. Please note that what we are discussing in this case is infrastructure as a service. I have explained them in the first chapter, but I'm going to explain them more deeply in the next slides. But what we are discussing so far is just to providing an operating system, an infrastructure, a virtual infrastructure to the user. That's why it's called infrastructure as a service. Now, if we want to do higher level services like platform as a service, for example, we give a programming environment to our users, then that platform as a service itself may be using um, uh, an infrastructure as a service in the underlying layers. All right. So we are pretty much done with the virtualization, with the VMs, in fact, with the VM as the main virtualized platform. However, I would like to mention that uh, over the past few years, there has been other virtualized methods as well, or other virtualized platforms as well. Conventionally, we know virtual machines, they have been with clouds ever since, but recently containers have come to play. So the main disadvantage with uh, virtual machines is their overhead. Although they are great in the sense of isolation, they isolate users from each other, so each user can have its own VM and feels that it has its own computer. But in fact, they have a heavy overhead. Just look at here that we have the hardware, of course. On top of that, we have hypervisor. On top of that, we have the guest operating system. On top of that, we have the application. So we have at least 3 layers of overhead. Each one of these layers impose some overhead. In containers, you can consider it as a lightweight virtualization. We just have the overhead of the host operating system, and then we have the container. It's a lightweight virtualization, and then within that we have our applications. So this is much lighter weight than VMs. They are instantiated in a matter of milliseconds, whereas here the instantiation takes a couple of minutes, and then they are kind of more agile. I should note that they do not provide isolation in the level that VMs provide, but they are still provide a good amount of isolation between users. However, the main advantage is their low overhead. This is called as OS virtualization, whereas virtual machines are called hardware virtualization. So here, all the containers share the same OS. So basically on your hardware, let's say you have Ubuntu, and on top of your Ubuntu, you have multiple containers. You can have multiple containers. So therefore, all those containers share the same kernel. They share the same operating system. All of them are Linux-based. Then you may ask, what is the isolation? Where is the difference? Where is the things for each user, which is basically the isolation? The isolation is on the package level. Let's say in this case, you can have two users, each one of them running a Python program with a different Python uh, version. Probably you have encountered a situation where, let's say you have a Python program that is written in, let's say, version 3, but the one that is installed on the machine is version 2.7, or vice versa. So in this situation, you should basically upgrade the Python on the host machine. But in that case, some other applications cannot work. So the solution is that you have your own container. In each container, you have isolation at the package level. So the softwares and the packages that you have in each uh, container is separate than others. So you can have Python 3 on your container A, and another user can have Python 2.7 on another container, and you both work with the system, you both use the same operating system, and it is much lighter weight, and it performs much better. All right. So a little bit about nomenclature of container, where the word container is coming from. You can imagine an old shipping style in which goods were carried, in a bulk way and without any container. And of course, in this way, there was a lot of problems. So let's say the items can leak from one to other, and there were more risks in shipping them. The modern approach, however, is to put the goods in different containers and give them some isolation and protect them from each other. So the name containers comes from this idea that we can put different uh, packages within different containers. All right, so let's go a little bit deeper and talking technically how containers are created. I would like to mention that containers are nothing but uh, using two services of the host operating system, known as namespaces and C groups. So using these two services of the host operating system, the concept of container is created. In fact, there is nothing called container. Container is just the aggregation of these two host operating system services. Now, let's see what are these services. What is a namespace? A namespace is in an operating system uh, is is a module of operating system which is in charge of restricting the visibility or isolating processes from one another. For example, imagine that you have a threaded application that has spawned multiple threads, and so those threads all have access to the same part of memory. They all probably have the same range of process IDs. So each process has a process ID. So they have to be protected from other processes. They can share some memory, some resources, but others cannot share anything with them. So basically, we put these processes together within a namespace. We can say, as you can see in this picture, we can say you can draw a circle around the process and its belongings, and this is a namespace. Or let's say you have an MPI application. Well, MPI is a little bit different. We can say an MPI that is running on one machine with multiple cores. So it creates multiple processes, and these processes are all belonging to one MPI process. So all of them are under the same namespace. So basically, restricting the resources in containers are taken care by this namespace module. Another module of the host operating system that is useful is called control groups or C groups. C groups is a kernel module, and its job is like a police. So the job of it is being careful that a process does not go beyond the resources it is allocated to. For example, if a process is allocated memory like 1 gigabyte of memory or 100 megabyte of memory from this address to this address, from address A to address B, let's say, uh, then how do we know that this process is not going to write on another process memory? So C group is in charge of this operation, this restriction. It is actually policing. It applies the restrictions. It follows the processes and makes sure that they do what they are supposed to do. So, um, so yes. So using this, defining C groups for namespaces, assigning C groups or to these namespaces create the concept of container. That is why we can say a container is nothing but the aggregation of namespace and C groups. Well, I should not say aggregation because they are not aggregated, just combination of them together. Nowadays, there are several container technologies, and by the way, container is one of the cutting edge technologies of clouds, and they are becoming very, very popular nowadays. One of the container technologies that you may have heard of is known as Docker, and there is a platform like a hypervisor in for VMs. Here we have something called Docker Engine. So that basically its job, so you install Docker Engine on your machine and it enables you to create Docker instances, each Docker instance being a container. There are other platforms, for example, Singularity is becoming very popular, OpenVZ and LXC, which is a native containerization technique in Linux. So now you have the concept of container. That's another form of lightweight virtualization. So how to deploy that? Of course, you have a bare metal. When you say bare metal, it basically means the host OS, the host machine plus its operating system is known as bare metal. And then you can apply containers on top of it. Another approach is that, which is actually very common nowadays in clouds, is that you have bare metal. On top of that, you have VMs, and then within VMs, you have your containers. This has become very popular recently as a method of allocation in clouds. Okay, so again, if you want to deploy containers in large scale, let's say on a cluster, okay, each node of the cluster would have a Docker engine and Dockers. Then you need something across the cluster that manages the whole thing for you, the whole containers or the whole Docker engines, let's say if you use Docker for you. So this is called container orchestration. So Again, it has similar responsibilities to those that OpenStack or OpenNebula has, but it is more towards containers. The very popular the very popular orchestrator nowadays is Kubernetes. That is a product of Google. It's open source though, and it is being extensively used. There are other platforms like Docker Swarm or Apache Mesos, but Kubernetes is getting more popular nowadays. All right, with that, we can wrap up the virtualization part of this chapter. This is an important part of this chapter. We talked about the fact that virtualization eliminates or decouples the hardware from software layer, from the operating system layer, or from the package layer, from the application layer. And it can be done in form of VMs and containers. So some benefits, a summary of benefits of virtualization is as follows. They increase the portability and flexibility. So I guess we are all convinced with that. We talked about consolidation. We talked about basically migration. And they provide cross-platform compatibility. So basically, if you have an operating system that does not work with a certain hardware, it may be able to work with the virtualized layer that is the hypervisor basically. It increases the security because it provides more isolation between users. Very, very great feature for cloud users. And it simplifies migration. This has been a dream for system admins for a long time. And support of legacy applications. Note that this is one of the usages of virtual machines. Let's say you have, it happens a lot in industry, that you have a proprietary software that just works with Windows XP. And of course, nowadays you cannot easily find Windows XP or a machine that easily works with Windows XP. So what you can do is that having Windows XP as a virtual machine and then deploy your application within that and then run your virtual machine wherever you like. And then, of course, isolation that we already talked about it as another advantage of virtualization. All right, we conclude this session here. Next session, we will talk about other advantages of virtualization, other enablers of cloud platforms.